talk, which will be by Guillaume.
Yeah.
Okay, whenever you're ready.
I'm going to share. Oh, where is it? Okay, here it is. Great. Okay. Hello, everyone. It's cool to have a lot of people for Buffet. I'm going to talk a bit about what we do in COD ACCRA and the results we have so far. But first of all, I would like to thanks people and participants of COD ACCRA because they are really motivated and they do a great job. So major part of what I will present is their work. Okay, so here, first of all, for people who are not expert of climate modeling, I just recap a bit what we're talking about to be on the same page. So we talk about 1D vertical climate models. So the idea is to have one single atmospheric column, which is representative of the entire 3D-ness of the atmosphere. So it's quite simple models, but it's also super easy to use, and it's I think the first climate models we developed historically. So they are simple, yes, but they're very useful and very fast to compute. So they're largely used and they are also used to link the atmosphere with, for example, the interior of the atmosphere or to model atmospheric escape and so on. So even if they are simple, they are important for a lot of scientific questions. So let's see what we have in these kind of models. So first of all, we need a temperature profile. So we can compute this using different equations, assuming that the troposphere is at the convective equilibrium, and usually we have an isothermal stratosphere. By knowing this, then we can compute excuse me, the relative transfer in the atmosphere uh, and the thermal emission of the atmosphere, but also the flux which is absorbed by the atmosphere, accounting for Rayleigh scattering, for example. We can also add several parameterizations in the atmosphere to mimic the effect of the clouds, for example, both regarding the thermal emission of the planet, so the greenhouse effect of the clouds, and their albedo, uh, modifying the bond albedo of the planet, I mean. We can also add, for example, photochemistry at the top of the atmosphere. So here, the main quantities we compute are the flux which is absorbed by the atmosphere, the ASR, and the thermal emission of the planet, so the OLR. We can also then, when we have these two quantities, we can have a loop over time, meaning that we modify the thermal structure of the atmosphere to try to reach the equilibrium between the flux which is absorbed and the thermal emission. So here we talk about time marching modeling. So it's basically the same model with the same physics, but then we wrap this in a loop over time to have a temporal evolution of the atmosphere to reach the equilibrium. So regarding the roadmap we have so far, we have basically three steps, increasing in terms of complexity to try to include as much bundles as possible. So the first step is quite simple, without any temporal evolution. So we have a lot of cases for this. The second step we have a selection of cases, and we focus on time marching modeling. And for the third step, still time marching, but with more complex cases. So the idea behind this is to allow a lot of people to join and to do simulation for this, whatever the capabilities of the model. So some models could do only the cases of first step. Some others could do every steps or just doing time marching and not inverse modeling. This is also possible. So regarding more precisely at the cases we have for the three steps. So for the first one, we have quite a lot of different cases. So we have the Earth, we have the modern Earth, we have Venus, because it's interesting to compare the Earth and Venus always. We have also the onset of the honorary greenhouse, which is studied since quite a long time now with this kind of models. So as there is a lot of paper in the literature talking about this, it's interesting to compare the models on this specific case. And we have also CO2 rich atmospheres and CO2 condensation that is usually the outer edge of the habitable zone. So with the onset of the honorary greenhouse and CO2 condensation, we have a comparison for both the inner edge and the outer edge of the habitable zone. For the second step, we have for now only Mars, Venus, and modern Earth because the time marching models are a little bit longer to run than inverse modeling, which is kind of instantaneous. And for the third step, it's also time marching, but here we have quite more complex cases, especially hot Jupiters and warm sub-Neptunes. So the difficulty here is that as there is a puffed atmosphere, the thermal inertia is quite larger, and also especially in hot Jupiters, we have a very specific species and chemistry and some complex stuff happening. We suggested also magma ocean planets. And of course, the TRAPPIST-1 system, because it's kind of largely studied in the community. So this is what we have so far. And for the protocol paper, we selected just a few cases. So modern Earth as a kind of benchmark simulation for both inverse modeling and time marching modeling. So we consider water, nitrogen, and 400 ppm of CO2. We share the same PT profile. So for inverse modeling, we have the same PT profile, and then we compute the absorbed and emitted fluxes. And for the time marching, we have the same initial PT profile, and then we let the system evolve. So I mean, the final PT profile is not the same. Because we have temporal evolution. We assume 6% of relative humidity, and we do not share the same opacity data. We have a discussion about this. So for now, the results we have, we use the native opacity data from every model. It could be interesting also to have a simulation sharing the same opacity data to see the difference coming from the opacity data and the difference coming from the modeling of the processes in the atmosphere. But it's not straightforward to share the opacity data because they are not necessarily at the same resolution. They are not necessarily the same kind of data as well. Well, it's still in discussion at this point. And also, so this is a kind of easy modeling, this modern Earth case. And we also have a more complex case to highlight the fact that we need a lot of model to join this effort. And this is TRAPPIST-1G. And basically the idea is to study kind of CO2 dominated atmosphere, quite cold to see CO2 condensation maybe. So we started to discuss this this summer, and we still need to do the simulation. I mean, to properly fix the conditions we would like to have for this case, and then run the simulations. And yeah, for this case, the idea is not to properly explain the differences, but to highlight that complex cases need a longer explanation and need more models to discuss the processes. So let's see what we have so far. So here we talk about inverse modeling, so no temporal evolution. So we all have the same PT profile, and we look at differences on the radiative transfer. So you look at the OLR and ASR as a function of the altitude, so the pressure, for different models we have in COD ACCRA. So we're pretty well in accordance. Just for EOS, there is a large difference in the ASR because we don't compute it exactly the same way. So we are in discussion to solve this, and the final output should be quite the same than the others. And also in Klima, the OLR is a bit different because if I remember correctly, we don't compute the relative humidity the same way. Yeah, I think it's this. But well, these 2 points are in discussion, and except that there is not much differences here. Knowing that we don't have the same opacity data, so that means the opacity data we have are quite similar at the end. We did the same simulations on moderners, but with time marching now. So on the left are the OLR and ASR, as I showed just before. At the middle, you have the final temperature profile obtained by each model. So it's quite similar in the troposphere, so close to surface, except for the generic PCM, but we discussed about that, and if I remember correctly, the quantity of CO2 we assume is not the same. So that's why in GPCM, the surface temperature is quite low. And we have some differences of temperature in the stratosphere coming from the way we compute the relative humidity in the different models. So this is the last panel on the right. So the mixing ratio of the water of the total pressure. And it's pretty similar in the troposphere, so close to surface. And as you can see, there is kind of large differences in the stratosphere. And this, from my point of view, this is quite interesting because they had comparisons of GCM in the past. It's a paper from Jeremy Young, 2016, if I remember correctly. And one of the outputs was to say that between GCM, one of the major differences come from the fact that they don't compute the relative humidity the same way in the stratosphere, and that's why for certain GCMs there is a moist greenhouse, and for others there is not. So yeah, it could be interesting if we could have some insights on this point by comparing this. Okay, and we talked about synergies at the during the introduction, and Kostas talked about that as well. So we started a discussion with the peoples from Pi, and so we discussed about this a few times the past weeks. And one possible collaboration could be that someone in COD ACCRA computes PT profiles for specific conditions, and then people from Pi use these PT profiles to compute the photochemistry. So there is, we think, a lot of stuff to do. It's just the beginning of the discussion, but yeah, stay tuned for this. Uh, there is also maybe another possible collaboration because in COD ACCRA we talked about differences in opacity data we use, and one question was to know if we would like to compare directly the opacity data or not, because it's quite of a huge task, and it's also kind of Pandora box. But as far as I know, they did this in Malbec. So maybe at some point we could discuss with Malbec to know if they have some outputs or guideline or something to say about this to help us to understand the differences we could have in the radiative transfer coming from the opacity data directly. And also, I thought about that during the introduction by Thomas, but Tim would like to create a new group for interior modeling, and this could be also an interesting, very interesting collaboration, because a hot topic there is in the community is to try to link the interior with the atmosphere, especially for planetary formation and the creation of the secondary atmosphere. So this could be quite interesting to discuss this as well. So yeah, looking forward to this. And finally, I will conclude with the recipe of COD ACCRA if you want to make this, cook this by yourself. Thank you very much. I will take questions or suggestions if there is. Thank you.
Thank you very much, Guillaume, especially for the recipe. Great stuff. So Thomas had a question regarding the synergy between Malbec and COD ACCRA, but I feel like you partly answered Thomas' question. Thomas?
Yeah. Yeah, Guillaume, yeah, great. Thank you. Yeah, I was wondering concerning, what you mentioned, like the discrepancy of the opacity data. So could it be possible to do like we have done in Malbec, which is having sort of one universal file and then having a script, a single script that will convert this file to whatever format is required by the code. And so that would be essentially the same flavor than the Malbec file, but this one would be a sort of the COD ACCRA file.
Do you mean for the opacity data or
Yeah.
for the outputs? The opacity
The
data.
opacity data at the beginning, yeah.
Yeah, I think it's possible. What we discussed so far is that we would like we could try to merge or to switch from a format to another using ExoK because especially it's a package which is very useful, especially for dealing with K tables, and I think most of our models use K tables.
Yes, some code have line by line as well. That's why I was wondering if like you grab the same opacity source and then the script will do the conversion to whatever is required by a code. I don't know if it's feasible, but definitely something that has been done for Malbec, not for opacity per se, but because I'm wondering in the case of COD ACCRA, there are a lot like the differences between the opacities and what is within the physics of a code are both like I must say equally important, and they are going to really change the outcomes if we if we don't, try to be more uniform in terms of opacities.
Yeah. I mean, to do this, we need to start from kind of state-of-the-art opacity data and then downgrade them to match with every model. Because this is possible, but if we start with some random opacity data from someone, and then another model needs a higher resolution, for example, then it's not possible.
Okay.
We can only downgrade the resolution, but we cannot increase the resolution and kind of create information in the opacity data. So this could be possible only if we start from creating the data, basically, I think.
Mm-hmm. Okay. Yeah. Tomorrow, Geronimo is going to talk about Malbec. He's going also to say a few words about another intercomparison effort that is from Exopag, and where they were really focusing on the opacity data at the beginning. It's for retrieval, but we realize you need the line list at the full resolution, and then after being done, and that's maybe the same way here. Thank you.
Yeah, but I think a first step going that way is just to discuss all together to have some kind of guidelines of the main difference they found because they did a large part of the job. For example, I don't know, does yeah, I forgot the word.
I mean, risotto?
No, the different oh well, whatever. Sorry, it's quite late here. Maybe that's why. But yeah, I mean, I'm pretty sure we have a lot of work to learn, a lot of stuff to learn before going to proper calculation on our side.
Okay, thanks.
Thank you very much, Guillaume.
Thank
Right.
you.
Are there any other questions to Guillaume or to previous speakers or in general? If not, I guess we can go to break a bit earlier. So yeah, go have a